Everybody, this is David Salatka with a new chemistry video on phase diagrams. This will be pretty quick and straightforward. So looking here, we have heat energy on the x-axis and a temperature of a substance on the y-axis. And what you're going to notice is this little zigzag pattern right here. So what the heck is going on? Well, let's pretend I have something like ice, which is solid water. That says solid right there. If I have ice and I add heat energy to it, well, obviously the temperature is going to go up. If you add heat to something, it makes sense that the temperature goes up. So right here, this is my temperature. It's going to go up and up and up and up and up, until we get to this point. Well, what happens at this point? Well, this is kind of weird. So the temperature actually flatlines because you have what's called a phase change. You're either melting or you're freezing right here. Well, if you're melting, all of that heat energy is being used to actually melt the substance. And what that means is the heat energy is literally breaking the intermolecular forces that hold a solid together. It's weakening them. So your heat energy is going to weaken those IMFs all the way until the water is no longer a solid. That means whenever ice is melting, it stays at 0 degrees the entire time. Then, once it's fully a liquid, guess what? Your heat energy just increases the temperature again. So up and up and up and up and up until you get right here. Now this is very interesting because when you cook in the kitchen and you boil water, the temperature never ever exceeds 100 degrees Celsius. That's really important to know. That's why we have other cooking styles other than just using boiling water. So we're either boiling or vaporizing. That's the word I use. And then going the other way is condensing. So you go, and all the way until you are fully boiled. Once you're fully vaporized or boiled, you become a gas. In this case, you're steam. Steam can be a lot hotter than 100 degrees if there's no water left over. Like nuclear power plants have steam that's hundreds of degrees Celsius. So that's kind of how this works. Pretty straightforward. Coming over to this one's not on your test, but this is also good to know. Pressure and temperature, we call this a PT diagram. If you have very, very high pressure of something and decently low temperatures, you're at a solid. Keep in mind that states of matter they have to do with both pressure and temperature, not just temperature. So pressure kind of forces molecules together, and that is why the IMFs are stronger with more pressure. Because pressure literally pushes molecules together. As you get higher in temperature, and you still have decent pressure, you're a liquid. Liquids are cool because it's kind of in the middle. And then gas is when you have pretty high temperatures and very low pressure. Now, if you notice, if you have almost 0 pressure, and you still have a very low temperature, you're actually a gas. That's why in space, even though it's so cold, you have almost no pressure in space, so everything's a gas, except for the planets, like rocks and stuff. But most things in space are gases, and it has to do with this whole, low pressure, low temperature thing. Alright, something even cooler is this point. This is called the triple point. And at the triple point, a substance can exist in all 3 states of matter at the same time. So if you look up the triple point of water, you can actually see it. It's pretty cool. It's at a very specific pressure and temperature. If you change it a little bit, you immediately leave the triple point. And then way over here, this is the critical point. After this point, nothing can really exist. At this point, you have neither a liquid or a gas, and very strange things happen and the laws of physics are broken. So there you go. That's states of matter. I hope you enjoyed, and good luck tomorrow.